Right, good morning everyone. So we'll continue the lecture for today. So today we were going to do the last part of chapter 4, and then we have already, we'll finish chapter 4 by today lah. Alright, so I think what you have done so far, you have already covered most of the difficult parts of chapter 4. Since we already covered the equation for bash, equation for PFR, and we completed half parts of the equation for CSTR. So perhaps if you remember what we have already covered in part 1 and part 2, you can see that actually there's a lot of equation, right, that you learned in chapter 4. So if I were you, of course, it's a little bit overwhelming when we have so many equations, but it's okay. So later when we do questions, actually you can really see the situation of which the equation apply. Dia taklah susah sangat, tapi at this stage where you first learn or you first get familiarized, it can be a little bit overwhelming. Tapi as once we do tutorial, then you can see that actually it's not that difficult. Right. So today I'm going to finish the last part of CSTR. So CSTR last Monday I've already covered for liquid phase, right? So today I'm going to finish up on the gas phase. Okay, so sama je konsep dia. Bila kita nak, when we develop equation, design equation for reactor ni, there are only 3 criteria that you have to check. Okay, one is definitely the types of reactor, kan? Sebab different type of reactor, design equation dia dah berlainan. Okay, so that's the first criteria. So whenever you see question, you have to really see ini adalah batch reactor ataupun CSTR ke or PFR. Okay, because the types of reactor, definitely the equation is completely different from one another. So that's first. Second, dah kena tengok phase dia. So remember, kalau macam batch reactor is okay, but regardless liquid ke gas phase ke, dia punya equations are the same. So you don't have to worry when it comes to batch reactor. But when it comes to flow reactor, PFR and CSTR, you have to really see the difference in the equation for the design, solely because kita tahu concentration of your reactant A ke, reactant B ke, expressed differently in liquid and gas. Sebab concentration tu express berlainan, you can see design equation ni pun dah jadi lain. And third factor is rate law. So you pun tahu kan, reaction have different types of rate law kan. It depends on the nature of the reaction. So sometimes it can be first order, minus RA KCA. It can be also second order, minus RA KCA square, minus RA KCA CB. Tapi even then also you have to remember that we only learn the common rate laws. Okay, apa yang kita cover dalam kelas, what I cover in the class is a very common rate law. I did not cover all types of rate laws. So bayangkan if I cover third order ke, fourth order ke, the equations can be even more complicated. Okay, but that doesn't mean you're not learning all. It means that I covered the most common rate laws. That I think majority of the reaction that you will encounter are usually first and second order reaction. Okay, so we're going to do all over again how to derive the equation, all right? But this is for CSTR gas phase reaction. Okay, so of course we always start first with the very simple rate law, which is first order with respect to A, meaning the rate law is only involve one reactant, which is our reactant A. Okay, so the design equation for CSTR, okay, you already know this. Kalau dia adalah single CSTR, kamu kena ingat, this is only applicable for single CSTR equals to FA naught X per minus RA. So, kalau nak derive untuk CSTR is much easier kan? Sebab kalau batch PFR, it involve a lot of integration. So, it's a little bit difficult, I can imagine. But CSTR, they're very quite straightforward, right? So then second thing, we have already determined that we want to express for first order reaction. Sebab tu minus RA equals to KCA. Okay, and then third, we express pula CA in the form of CA naught dan X. So perhaps if you wonder kenapalah kita kena express, sebab as I told you, very rarely we actually measure the concentration of outlet. Usually we know the initial concentration because we prepare the solution, and we will know the conversion. Either it's a targeted conversion or from previous studies we know that is the conversion that we can achieve. Okay, so most of the time, that's why kita kena express CA dalam bentuk CA0 dan X. Okay, and then in the form of gas phase. Gas phase, and at this stage, we are still talking isothermal isobaric, meaning no change of temperature, no change of pressure. Sebab tu equation dia jadi CA equals to CA0 1 minus X per 1 plus epsilon X. Kalau dia ada perubahan tekanan, which we will do slightly later, dia akan ada tambahan P0 per P kat bahagian bawah. Dan kalau ada perubahan suhu, T per T0 tambahan lagi kat bahagian bawah. Okay, so you must understand at this stage, kita assume dulu tak ada perubahan tekanan, tak ada perubahan temperature. That's why it become 1 plus epsilon X only. Okay, alright. So then, what do? We just combine 1, combine 2, combine 3. So chapter 4 sebenarnya adalah combination of what you have learned in chapter 1, chapter 2, chapter 3. Okay, so when you combine 1 to 3, alright. So of course a little bit difficulty sebab the form of the equation becomes 3 layer. Dia macam A per B per C. Tapi konsep dia like I taught you last Monday, bila dia A per B per C, basically the bottom layer goes to the top, so become AC per B. Okay, so that's why you can see the 1 plus epsilon X now goes to the top, as you can see in the red font. So dia menjadi FA0 X in bracket 1 plus epsilon X per KCA0 1 minus X. And then remember, I told you before, sometimes, okay, it depends on information given to you. So you must understand, right? Macam dalam engineering ni, one of the challenges is that the information is not something that you can choose to have or not to have, kan? Contohnya macam, mungkin dalam soalan kamu kata, okay lah, sebab lecturer boleh pilih apa yang dia nak bagi, apa dia tak bagi, which is true. But even in real life, you know, it's sometimes information that you want are limited by the boundaries of your equipment measurement. So that's why I said, of course, in ideal case, kalau kita tahu CA kan senang kan, kita nak kira straightforward kan. Tapi as I said, the boundaries of the process, most of the time process tak akan measure CA. Okay, you will know CA not because you prepare solution, and you will know X, the conversion. So that's why it's something in engineering that you have to understand. Information doesn't necessarily comes in the way that you want. It's always limited by the boundaries of the equipment, boundaries of the system. Alright, so let's say lah dalam case yang kamu nak selesaikan ni, kita tak tahu FA0 dan CA0. Let's say the measurement of the equipment, you are unable to determine FA0 and CA0. Let's say, kan? Okay, so what do we do? Okay, so fortunately, you also know FA0 kalau bahagi dengan CA0 di bawah, you get actually what? Initial inlet volumetric flow rate, right? So let's say pula your equipment tu boleh tahu inlet volumetric flow rate. So there's a way for you to measure. So you know that kalau FA0 per CA0, you will get the inlet volumetric flow rate. So that's why the form 2 of the equation become V0 X in bracket 1 plus epsilon X per K 1 minus X. So that's why to find the volume, basically we have two different versions of the equation. So bukanlah untuk make your life complicated or just to tambah equation. This is just to for you to be aware that sometimes information you have to suit the equation or you have to change the equation. Bukan change, somewhat rephrase the equation according to the information given to you. So let's say kalau diberi kita inlet volumetric flow rate, you use the second form. If let's say given FA0 dengan CA0, you can use the first form. Okay, alright. Then the first two form is to find the reactor volume. Okay, then but sometimes you must remember that at times we want to know space-time as well. So remember sometimes in the system, in the reactor applications, we also would like to know, let's say, the space-time of the reactor. Kan? As I told you, kita pernah belajar kan, space-time is how long the molecule stays in the reactor before it has to flow out based on the initial condition. So let's say someone asks you, actually, apakah space-time untuk reactor itu? So you have to also know in the form of space-time. Tapi in the form of space-time is quite straightforward because you have learned kan, space-time tau is actually equals to what? Volume reactor divided by inlet volumetric flow rate. Okay, so daripada form yang kedua ni yang dalam green font, you can see that if I move my inlet volumetric flow rate from right to left, from my right to the left, it will become division kan. So volume akan dibahagikan dengan inlet volumetric flow rate. So automatic volume bahagi inlet volumetric flow rate is the space time. Okay, so at the right hand side akan tinggal x1 plus epsilon x over k1 minus x. So now you got the third form of the equation, of which the third form is to find the space-time. So depends lah, as I told you, sometimes they might also ask for space velocity. So saya memang tak letak equation untuk space velocity because as I said, I would like you to try to find yourself space velocity. Sebab kamu dah faham konsep dia, kamu tahu apa itu space velocity, apa perkaitan dia, you can easily express the concentration if it's for space velocity, SV. Right? Okay, so done for first order. Right. So next one we go to second order. So second order apa beza dia? Dz equation masih sama, concentration pun masih sama. Asalkan tak you don't change the phase, it's the same phase, concentration remain the same. You didn't change the reactor, design reactor masih sama. Tetapi if you change the rate law ataupun bukan change rate law lah, katakan dia untuk reaction yang baru ataupun katakan kamu kena faham, as long as you change any one of the reactant in the reaction, dia dah jadi reaction baru. And sometimes kamu kena ingat, even kalau menggunakan reactant yang sama, but you change condition, let's say temperature, especially temperature, reaction tu pun boleh berubah because it can go through different pathway or different mechanism. Contohnya, oxidation dan combustion. Kedua-dua tindak balas sebenarnya menggunakan oxygen gas. But if oxidation normally occurs about less than 200 Celsius. Tapi katakan kamu naikkan suhu tindak balas tu kepada let's say above 600, menggunakan bahan raw material the same, it can be combustion. Dia akan berubah menjadi combustion apabila ia adalah pada suhu yang tinggi. So kamu kena faham, kadang-kadang tak tukar reactant pun tapi tukar perubahan, you change the temperature. Most of the time temperature, it can also be a different reaction. So bila dah reaction yang berlainan, rate law dia pun akan jadi totally different. Okay, so tu yang kamu kena faham. Sometimes saya kata reaction ni complex in that sense. Saya tak tukar raw material, saya tukar temperature pun dia dah jadi tindak balas berlainan. Means kalau tindak balas berlainan, rate law berlainan, the entire Dz equation dia pun dah jadi berlainan. Or let's say you use the same reaction, okay, katakan dia lah menggunakan raw material yang sama, but instead of in the liquid phase, kamu pergi guna dalam bentuk gas phase. Also, it can be a completely different reaction. It can be completely different design equation. So very, very important to bear this in mind when you really work in a real application. When you want to do any changes in the reaction, kamu kena aware that it has a very big implication towards the design reactor and towards the performance of your reactor as well. Okay, so I come back to here. So now you imagine now, tadi kita buat tu untuk first order, right? Now let's say I change, it comes a second order reaction, meaning minus Ra equals to KCa square, meaning the reaction tu rate law dia, kadar tindak balas dia bergantung kepada second order of your concentration A, okay, KCa square. So we combine equation 1, equation 2 dan equation 3, and then we will simplify back, and eventually we will get back the design equation in the form of 1, in the form of 2, in the form of 1 in the rate form. So rate form tu again dalam bentuk Fa0 dan Ca0 if you know both of this value. And let's say you don't know and you know inlet volumetric flow rate, you can use the second version in the green font. And the third form is when you want to find space-time. Okay, so you can see that dia definitely design equation dia akan berubah lah kan, sebab rate law dia tadi KCa, sekarang dah KCa square, automatic when Ca tu dah menjadi kuasa 2, equation dia pun akan berubah. Okay, so remember kalau dalam test, dalam exam, as I told you, you don't have to memorize. Memang that's the good thing, tak payah memorize. Tapi make sure you tengok betul-betul equation tu, and most importantly, make sure you calculate correctly. Sebab mungkin kalau kita tengok equation tu nampak macam senang nak tekan dalam calculator. Tapi trust me, based on your seniors experience, most of the time dia ganti nombor yang betul tapi half of the time dia akan dapat jawapan akhir yang tak betul sebab dia tak aware ataupun dia kena dia leka. There's a lot of bracket and sub bracket and there are multiplication, division, you see power of 2, power of 3. So you have to be very careful when you are doing the calculation, right? Okay. So next one, okay, the last rate law that we will cover is KCA-CB. Okay, so this rate law yang biasanya paling panjang lah because now kita melibatkan dua reactant sebab kadar tindak balas dia sekarang bergantung kepada depends on reactant A, reactant B. So kita dah kena express pula concentration A and concentration B. So nak express concentration B ni kalau kamu masih ingat dia kompleks sikit kan sebab it become CB equals to CA0 in bracket theta B minus B per AX per 1 plus epsilon X. So dia a bit complicated lah sebab dia punya concentration B tu express slightly different compared to A. Okay. So part ni yang kamu kena ingat. So dalam soalan kamu kena tengok betul-betul rate law dia. Adakah dia minus RA KCA, minus RA KCA square, minus RA KCA CB. So kamu tengok rate law yang berlainan, design equation dia definitely becomes very different. So same concept. You combine design equation, you combine rate law, you combine the concentration, you will eventually get the three main equations, of which the first equation is for the, if you know FA0 then CA0. Second form, if you know inlet volumetric flow rate, and the third form is to find space-time. Okay, so it's imperative, it's important for you to understand kenapa ada banyak equation. So bukanlah sebab nak sengaja buat banyak equation, but I told you is the limitation in exam test. Perhaps you can say itu adalah apa yang lecturer nak uji student. But in the real life, this is also applicable because as I said, your system, your plant, your equipment will have certain boundaries of measurement and you have to actually able to see how you can rephrase your equation to fit to the boundaries of the equipment measurement or the system itself. Okay, so we are done on the design equation. So I think kalau kita kira balik memang adalah kan dalam 40 ke 50 equation dalam chapter 4. Okay, don't worry. Chapter 5 tak ada sangat. Chapter 5, chapter 6 actually not that difficult. Chapter 4 sebenarnya chapter yang paling susah lah. And chapter 5 and 6 very straightforward. It will not be as difficult as chapter 4. Okay, so done on design equation. Alright. Tetapi remember I told you yang tadi kita belajar tadi dan juga last Monday we have learned all the 50 and 60 design equation, right? Tapi in all that design equation I already told you that we are assuming now constant temperature, constant pressure. Okay, so sebab kita nak buat benda ni dalam stages dahulu. Okay, so now kita dah cover part when reaction tu tak ada perubahan suhu, tak ada perubahan tekanan. Okay, but you have to remember kan, in a world, in the ideal world, memanglah kita harapkan tindak balas tu tak ada perubahan suhu, tak ada perubahan tekanan. But realistically, there are reactions of which they may be change of pressure, change of temperature. Kita tak boleh elak kan sebab in the real world memang macam tu. Ada tindak balas will involve the change of pressure, change of temperature. Okay, so how does it affect our calculation? Adakah dia mempengaruhi pengiraan kita? The answer is yes, but at certain rules and regulation or at certain caveat. Apakah maksud dia? Okay, maksud dia adalah if you are dealing with liquid phase reaction. Okay, sebab tu sekarang saya kata kalau let's say you work in the real world, real plant, kalau your reactor tu processing liquid phase reaction, you should be very thankful sebab liquid phase reaction ni quite more straightforward, senang sikit compared to gas phase reaction. But if you're dealing with gas phase reaction, you have to know the additional headache will be there. Sebab gas phase reaction ni is influenced by many of the property. So the same as this case. If you're doing on liquid phase, perubahan tekanan tak akan mempengaruhi kamu punya tindak balas. Okay, tapi of course kamu pun tak boleh juga tak tengok langsung perubahan tekanan sebab in your reactor, you know right, reactor we have certain material of construction and all of this material construction ada limit pressure dia. So you have to still monitor the pressure in your reactor Just that, kamu tak payah bimbang outcome conversion tu ke, the concentration of your product ke, kamu tak payah bimbang. Dia tak akan dipengaruhi oleh perubahan tekanan. But that doesn't mean you don't have to monitor the pressure, because material construction of reactors, any kind of material that you use, it can be carbon steel, stainless steel, it can be glass, whatsoever, it still have its pressure rating, pressure limit. So tak bolehlah biar je kalau accumulation of pressure, increase of pressure can also cause serious issue, severe issue towards your reactor. Okay, so that's the story lah. Right. On the other hand, kalau dia gas phase reaction, effect of pressure must already be considered in your design of reactor. But ada pula dia punya limitation. Kalau gas phase reaction tu dalam batch reactor, dia tak mempengaruhi design reaktor kamu. Okay? Sebab kalau dalam batch reactor tu, assumption dia, kita assume volume reactor tu takkan berubah. Inlet outlet volume reactor is the same regardless of the pressure change. Hence, the design equation is still the same. Ingat tak, kalau batch reactor design equation tu kan kita kira reaction time kan? So maksudnya, tindak balas tu liquid atau gas pun dalam batch reactor, the reaction time will not be affected by the change of pressure in your batch reactor. But if it's a flow reactor, which is PFR, CSTR, okay, this will have a severe consequences towards your design reactor. Sebab in gas phase flow reactor, it will influence the volumetric flow rate. Ingat kan sebelum ni kita assume inlet volumetric flow rate sama dengan outlet volumetric flow rate. But when there's a change of pressure, this will affect the inlet outlet volumetric flow rate. Sebab tu kita dah pernah belajar equation ni. This equation says outlet volumetric flow rate equals to inlet volumetric flow rate in bracket 1 plus epsilon x. So sebelum ni bila tak ada perubahan tekanan, kita stop kat sana kan. But if now there's a change of pressure, now you have to include P0 per P dalam equation tu to address if there are changes in pressure. Okay, so particularly pressure drop lah. Pressure drop tu maksudnya apa? Maknanya ada outlet pressure, your P is lower than your inlet pressure, P0. Okay, so not necessarily saja pressure drop lah, pressure increase pun boleh berlaku juga. Okay, tapi the tendencies of pressure drop is more. So sama je konsep, pressure drop ke pressure increase pun tak apa. Ia is still equation is still put it as P0 per P. So kalau ada pressure drop, P tu lebih kecil daripada P0. Kalau pressure increase, P tu lebih besar daripada P0. Tapi regardless salah satu condition pun, equation tu masih P0 di atas, P di bawah. So you might wonder, how it influence our design equation kan? So tadi equation kita dah belajar yang 50-60 equation tu, apa yang berbeza? Kita just kena sekarang tambah part P0 per P tu dalam equation. Okay, yang ingat saya dah expresskan untuk kamu kan yang gas phase untuk CSTR, gas phase untuk PFR, setiap rate law tu saya dah pernah express kan. Tapi just part yang P0 per P tu saya tinggalkan tadi. But sekarang saya dah kena letak, saya dah kena, I have to add on the P0 per P in the equation. So I did not show you back how to express one by one. I terus summarize in this slide of the equation of which for each rate law, untuk setiap condition, untuk first order reaction, untuk second order reaction. So for PFR, as I told you kan, sebab equation dia panjang kan, so kita hanya cover rate law, KCA, KCA square. So you can see dia punya equation become more complex bila kita dah involve the change of pressure in the equation. So this is for PFR. The next one is for CSTR. So you can see kenapa saya cakap tadi equation tu jadi dah bukan 50-60, dah jadi 70-80 equation kan, because of this. Okay, so I can understand it can be very overwhelming. Tapi as I told you, tak apa. Nanti bila kita buat tutorial, you have to able to tengok. Okay, kita analyse apa information yang penting when kita nak select equation yang betul untuk solve problem itu. Okay, so at this stage, if you feel overwhelming, it's fine. Okay, when we do tutorial, then you will see clearly apakah sebenarnya benda yang kita kena tengok sebelum kita nak tahu equation untuk dipilih. Right, so done on this. Right, so the last part for chapter 4 is satu lagi benda baru yang kamu kena belajar. Okay, sebelum ni, okay, kamu belajar rate law untuk tindak balas that we call it as irreversible reaction. Okay, tindak balas yang tidak berbalik, tindak balas yang sehala, forward direction. Sebab tu kita dapat rate law. Minus RA equals to KCA, KCA square, KCA CB. Okay, semua tu adalah untuk rate law kalau tindak balas dia is irreversible. Okay. However, there's another types of reaction yang kita panggil sebagai reversible reaction. Okay, apakah itu reversible reaction? Okay, so kalau irreversible, straightforward kan, tindak balas dia hanya akan berlaku pada forward direction of which your reactant will react forward to produce product. So for example, katakan kamu ada reactant A dan B, kalau dia tidak balas irreversible, it will form C and D. Itu irreversible. Kalau reversible pula, the reaction occurs in both forward and backwards direction. Maksudnya, the A and B can react forward to form C and D. At the same time, C and D can also react backwards to form A and B balik. So tindak balas dia berlaku ke hadapan, ke belakang, forward, backwards, backwards. So you might wonder, susahlah kan nak design reactor, macam ni kita nak tahu bila tindak balas tu ke depan, bila ke belakang, which is a very normal question. Okay. Dia tindak balas forward, kan tindak balas dia akan berlaku forward, backward. Okay. But it starts the reaction. Eventually, it will settle into what we call as equilibrium. Dia akan mencapai keseimbangan. What does it mean by equilibrium? Okay. Perasan tak kalau tindak balas forward, backward, kepekatan A, B, C, D akan sentiasa berubah kan? Kalau tindak balas tu forward, C and D akan bertambah. Tapi bila C and D tidak balas ke belakang, A and B akan bertambah. So kepekatan dia akan menjadi tak stable, tak stabil sebab dia akan forward, backward. But eventually when it reach equilibrium, dia mencapai keseimbangan, apa yang berlaku? Concentration of both A and B and C and D will remain constant ataupun stable. Maksudnya, kadar tindak balas ke hadapan dan ke belakang berlaku pada kadar yang sama, maka the concentration no longer change. Okay, so that will only occurs at what we call as equilibrium, or as they say, the rate of reaction is identically zero for all species. Or we can say minus RA equals to 0. Okay, so this it only occurs when it reach equilibrium. And every reaction akan ada masa yang berlainan untuk dia mencapai keseimbangan. Kita tak akan tahu, you have to do a studies for you to know bila sebenarnya dia mencapai keseimbangan. So how do chemists do? They measure concentration lah. Means let's say every 1 minute, dia ambil concentration, dia ambil liquid, dia ambil dalam, katakan kita buat dalam batch kan. Okay, they take out the liquid at 1 minute, dia check concentration A, concentration B, concentration C, concentration D. Dia tengok. Minit kedua, dia ambil, dia check lagi. Dia akan check sampai masa apabila kepekatan semua tu dah remain constant, then dia boleh conclude this is the equilibrium time. Okay. So when the reaction reach equilibrium, okay, kamu ingat tak kita pernah belajar kan rate of reaction kan? Kita belajar reaction dalam rate law kan, minus RA sama dengan KCA ke, KCB, KCA square ke, KCA CB, kita ada K kan? K itu adalah pemalah kadar tindak balas, reaction rate constant. But that K is reaction rate constant for the forward reaction. Tapi kalau dah reversible, dia pun ada K yang untuk backwards. K forward yang kita selalu belajar. Sekarang kita dah ada K backwards juga. Sebab C and D pun boleh bertindak balas menghasilkan A and B. Okay. So, dia ada K forward, K backwards. And at equilibrium, pada keseimbangan, the ratio of your K forward over K backwards is actually called as equilibrium constant, KC. Pemalar kadar tindak balas pada keseimbangan, KC, equilibrium constant. So equilibrium constant ni sama dengan the ratio of your reaction rate constant forward over reaction rate constant backwards. Okay, and this KC, kamu kena faham, is only measured after the reaction has reached equilibrium. Sebelum equilibrium kamu tak boleh kira Kc, dia hanya boleh dikira apabila kesemua kepekatan tidak balas tu dah mencapai keseimbangan. And this Kc can be measured in terms of concentration. Okay, using this equation, paling senang je equation nak kira Kc ni. Kalau rasa confused nak hafal, ingat aja Kc equals to ada atas ada bawah. The top one is the concentration of your product, all of your product at equilibrium. Kamu kena faham, bila kita kira Kc, kepekatan kesemua produk dan reactant must be at equilibrium. Sebab tu dia letak CCE, CDE. Maksudnya concentration of C, concentration of D at equilibrium. The E at the subscript E is to signify this concentration is measured at equilibrium. And then power stoichiometric coefficient according to your chemical equation. So let's say katakan stoichiometric coefficient untuk C tu adalah 2, let's say. Katakan untuk D 1. So dia akan menjadi concentration of C at equilibrium power of 2, concentration of D at equilibrium power of 1. Okay, itu yang atas. Yang kat bawah, concentration of all of your reactant at equilibrium as well. So kamu bila masa kamu nak tengok pengiraan kira Kc ni, kamu kena make sure pengiraan tu mesti pada keadaan equilibrium. Dia tak boleh sebelum mencapai equilibrium. Okay, so then sama concentration of your reactant A and B, subscript E to show that is at equilibrium. Power of your stoichiometric coefficient again for A, for B. Okay, so katakan tindak balas dia 1A, 1B. So it becomes CA power of 1 at equilibrium, CB power of 1 at equilibrium. Okay, so this is how we calculate equilibrium constant. So sekarang kamu belajar pula satu lagi constant yang baru, equilibrium constant, Kc. So Kc ni kamu kena ingat, kalau dia reversible reaction, barulah muncul Kc. Kalau tindak balas dia irreversible reaction, Kc tu takkan ada. Okay, right. So tu dah settle untuk part Kc. Okay, now next one. Okay, tambah satu lagi pening dia. Okay, kan kamu ingat kan saya pernah cakap dengan kamu kan, concentration dalam reaktor tu, jarang kan kita measure concentration outlet A, B, C and D. Kan, ingat tak macam tadi kita design equation, saya dah kata dengan kamu, kita jarang kira CA. Tapi kita tahu CA dalam bentuk CA0 dan X. Betul? So, same concept. Bila kita nak kira Kc ni, jarang pula, like I told you, jarang kita nak measure CA, CB, CC, CD. Okay, kalau dalam konteks yang reality, dalam lab, yes, dia akan buat benda ni. Tapi dalam the real plant, they cannot afford to do so. You know, they cannot afford to measure each time. Berapa A, berapa B, berapa kepekatan A, berapa kepekatan B, kepekatan C, kepekatan D. Okay, so itu they will always know in the form of CA0 dan X. So sama konsep untuk case ni, kita pun nak tahu concentration A, B, C, D at equilibrium in the form of CA0 dan X. Tetapi sekarang, dia dah bukan X. Instead, dia adalah XE. Kenapa XE? Mungkin kamu bertanya. Okay? I always have to imagine the question by my student. Why XE? Okay. Kamu kena faham pula. Pada dia mencapai keseimbangan, alright, when you reach equilibrium, okay, you will have a concentration of this reactant, right, and definitely concentration reactant product ni akan berbeza daripada concentration asal sebab tidak balas dah berlaku kan. But at equilibrium, the conversion tu is specific. We call it as equilibrium conversion, XE. So bila kita nak measure concentration A, concentration B, concentration C, concentration D at equilibrium, the conversion is now called as equilibrium conversion. And dalam tindak balas reversible reaction, the highest possible conversion is actually equilibrium conversion. Dia dah bukan 100%. Kan kalau saya cakap kamu, untuk tindak balas irreversible, the highest conversion untuk reactant A adalah 100% kan? Maksudnya semua A converted menjadi produk. Tapi kalau reversible, dia dah bukan 100% highest possible conversion. Instead, the highest possible conversion is your equilibrium conversion. Maksudnya kalau kamu tak kacau reaction tu, kamu biarkan saja tindak balas berbalik tu berlaku, dia pergi forward, backward, and eventually equilibrium, itulah conversion paling tinggi untuk reaktan kamu yang kamu boleh capai. Selagi kamu tak kacau sistem tu. if you let's say kamu nak naikkan lah equilibrium conversion tu, boleh, kamu dah kena kacau sistem tu. So there are certain things that you can do to disturb the system in order for you to maybe increase the equilibrium conversion, but not necessarily boleh. But if you don't disturb anything, eventually it reach what we call as equilibrium conversion. So this can be apa-apalah, depends lah, 80% ke, 90% ke, we don't know, it depends on the reaction. Okay, that's why concentration ni kamu kena tahu nak express dalam bentuk Ca0 dan Xe. So kalau kamu tengok, the equation looks very familiar, right? Sama je. Apa yang berbeza? Instead of X, kita guna Xe. Tapi pun kamu jangan lupa, it also depends, right? Tindak balas ni liquid ke gas? Sebab ingat tak, kepekatan untuk gas for flow reactor is completely different, right? Compared to batch dengan flow liquid. So bila kita nak kira equilibrium conversion tu, kamu kena apply balik apa yang kamu belajar tadi. Kalau dia adalah batch and liquid flow, okay, kita belajar kan Ca sama dengan Ca0 1 minus X kan. Tapi kalau Ca pada equilibrium, dia menjadi Ca0 in bracket 1 minus Xe. X tu semua dah berubah menjadi Xe. Okay, so kamu kena ingat reaction ni, bila kamu belajar, you can really see that dia memang related to one another. Tak apa yang kamu belajar kat chapter 4 sebenarnya dah pernah belajar chapter 3 ataupun mungkin belajar chapter 2. So you must really know how to relate all this chapter. Dia bukan chapter in isolation. Means kalau belajar chapter 3, tak tahu chapter 2 pun tak apa, tak boleh. Nak tahu chapter 3, kena tahu chapter 2. Sekarang especially in chapter 4, kalau 1, 2, 3 tu tak strong, chapter 4 memang a little bit of a struggle. Macam kamu tengok ni kan, saya ajar reversible kan, tiba-tiba saya kait pula balik kepada concentration yang kita pernah belajar di chapter 3. So that's why you can see it's not in isolated chapters, the chapters are closely related to one another. Okay, then next one, I also try express to you, for you, concentration dia kalau dia adalah gas phase flow reactor, of which the concentration at equilibrium, and saya tambah juga kalau dia ada berlaku pressure drop. So saya terus tambah part yang pressure drop. Kamu kena ingat kan, pressure drop akan hanya muncul ataupun perubahan tekanan punya part tu hanya akan muncul bila dia adalah flow reactor gas phase. Sebab tu kalau kamu tengok yang sebelumnya yang saya tunjuk ni, liquid phase dengan batch reactor and liquid phase flow reactor, kamu tengok tak ada kan, P0 per P memang tak ada. Dia tak akan mempengaruhi. Dia hanya akan mempengaruhi apabila dia adalah flow reactor gas phase. So tambahan lagi apa benda yang kamu kena belajar. Okay, so macam I told you, cannot memorize. It's impossible to memorize. It's important to understand. Okay, so later kita buat tutorial, you will get it better. Right. So now, let's say kita nak express sekarang Kc. Kita nak express Kc untuk this reaction. So the reaction is 2A to produce B and 2C. Okay, macam mana kita nak tahu tindak balas tu reversible ke tak? Of course, the first way is to read the sentence lah. Okay, of course they will write it. Okay, this is the reversible reaction or irreversible reaction. Or the simplest way, you can see in the chemical equation, anak panah tu, kalau dia forward, kalau dia adalah irreversible reaction, anak panah dia ke hadapan. Kalau dia reversible, anak panah dia akan berada pada dua-dua arah. To signify yang tindak balas itu can goes forward and goes backward. Okay, so let's say you want to calculate Kc. Kita nak kira equilibrium constant for this reaction. So you will write it as Kc equals to top is concentration of your product. So in this case, we have two product, B and C. So concentration of B at equilibrium, power of 1, because the stoichiometric coefficient is 1, multiply with concentration of C at equilibrium, power of 2, because the stoichiometric coefficient is 2, divided by concentration of your reactant A at equilibrium, power of 2. Okay, sebab tu sebelum saya pergi forward, saya lupa nak beritahu ni. Bila saya express yang concentration ni, kamu kena ingat this equation yang dalam kotak kuning ni tak fix equation. Kenapa saya kata tak fix? Ingat tak saya kata especially dalam case B, spesies B ni. Sebab kadang spesies B, dalam contoh reaction ni, saya berikan A dan B sebagai reactant, C dan D produk. Sebab tu, the concentration of B at equilibrium in this equation berada di bawah. Sebab dalam tindak balas ni, B adalah reactant. Okay. Tapi kalau kamu perasan, dalam contoh yang saya tengah bincangkan ni, in this example that I've discussed, kamu perasan B ke atas kan? Mungkin kamu kenapa pula B ke atas? Sebab in this reaction, B is now a product. Okay, sebab tu saya kata kamu tak boleh hafal equation ataupun tak boleh just refer tanpa tahu the exception to the rules. So that's the challenge of reaction. Dia ada equation tapi dia ada juga exception ataupun dia ada juga perubahan bergantung kepada reaction. So in this example, why B is at the top, why the concentration of B at equilibrium is at the top is because in this reaction, B is our product. Okay, so then once you have written the equation, now we express in the form of Ca0 dan Xe. So kamu kena ingat pula, kalau B is a product, concentration dia expressed as B per A Ca0 Xe. So kamu kena ingat kan, mungkin tadi baru saya ajar kamu kan, Cb sama dengan Ca0 theta B minus B per A X kan yang tadi saya ajar. Kenapa tiba-tiba sekarang jadi B per A Ca0 Xe? Sebab yang Ca0 theta B minus B per A X tu adalah concentration of B jika dia adalah reactant. Dalam kes ni, B is a product. So it become B per A Ca0 Xe. Let's say if you want to refresh back, tak faham part ni, pergi chapter 3, tengok balik part stoichiometric table. Then you will understand. Okay, for those who find this very hard to digest, very normal, as I always tell you, you go back chapter 3, you check part yang stoichiometric table. Right? Okay, so done. So concentration of C at equilibrium juga, we have learned kan, concentration of product, C mungkin kamu dah biasalah. Concentration of C equals to C per A, Ca0 Xe. Kalau dulu hanya letak X, sekarang kena letak Xe, bracket, kena power of 2. Kenapa power of 2? Sebab the stoichiometric coefficient for C is 2 divided by concentration of A at equilibrium, so Ca0 in bracket 1 minus Xe power of 2. Okay, so then when you rearrange back, you can do cancellation of your Ca0, you will get your final answer. Sebab yang macam kes ni, saya suruh kamu, contoh ni hanya untuk express. Okay, kalau kamu diberi nilai, let's say you know your Ca0, you know your equilibrium constant, you can already calculate Kc. So dalam soalan, when you have exam questions or later when you do mini project, kalau tindak balas tu adalah reversible and dia beri conversion, kamu kena check itu adalah equilibrium conversion ke atau conversion sahaja. Dia berbeza. Equilibrium conversion is the conversion at equilibrium. X conversion adalah conversion yang berlaku pada bila-bila masa sebelum equilibrium is achieved. So kamu kena faham, Xe conversion pada equilibrium, X is dalam tindak balas berbalik pun akan ada X. X tu apa? Conversion of your reactant at any time before it reach equilibrium. Contohnya lah kan, katakan tindak balas tu dia mencapai keseimbangan dalam masa 15 minit, let's say. So, if you measure the concentration at any time between 1 minute to 14 minute, conversion yang kamu kira tu adalah conversion yang biasa yang kita tahu, X. Tapi bila dia mencapai keseimbangan pada minit ke-15, kamu kira kepekatan tu, conversion tu adalah equilibrium conversion, Xe. Okay, so part tu pun kamu kena faham sebab biasa nanti dalam test exam, student akan jadi confused bila masa dia X, kenapa dia X, kenapa dia Xe. Okay, so done. Next part is rate law pula. Okay, sekarang kamu kena faham. Tadi saya perkenalkan Kc. Kenapa saya kena perkenalkan Kc? Sebab rate law dia sekarang dah ada Kc. Tapi kamu kena faham juga. Reversible reaction ni, dia macam irreversible reaction. Rate law dia ada elementary, non-elementary. Ingat tak saya ajar kamu, kalau tindak balas dia elementary, rate law dia kena tengok equation kan? Kalau dia non-elementary, saya kena beri information. Okay. So, same concept dengan reversible. Tetap means dia ada elementary, non-elementary. Tetapi dia punya pemahaman tu, kamu dah kena faham beza dia. Okay. Kalau this reversible reaction is non-elementary, kalau dia adalah non-elementary, katakan saya kata this irreversible reaction is a O-base, a non-elementary rate law. Sama je outcome dia, saya kena beri information dia. Contohnya saya kata it's a first order with respect to A, first order with respect to B. So kalau diberi information tu, kamu dah tak payah tengok dah. Reversible, irreversible sama je. Rate law dia saya dah beri, kamu ikut rate law dia. However, katakan saya kata dia adalah elementary rate law. Means this is a reversible elementary rate law. Rate law dia dah ada specific rule yang kamu kena ikut. Okay, again I repeat. Kalau dia kata the reaction obeys elementary reversible rate law dia ada specific rule yang kamu kena ikut. Apakah rule itu? Okay. Rule dia kata kalau dia adalah elementary, dia akan sama dengan minus RA, masih sama kan rate law kan? Tapi sekarang rate law dia menjadi equals to K, reaction rate constant yang kamu dah selalu belajar, K, in bracket, okay. First one is the concentration of your reactant, all of your reactant. Dalam kes ni, yang saya beri contoh ni, I have one reactant A, one product B. So bahagian depan dalam equation tu hanya concentration of A power alpha. Alpha is the stoichiometric coefficient of A in your chemical reaction. So Ca kuasa alpha. Katakan dia ada reactant B. So you have to do Cb power beta. Tapi tu kemudian. Sekarang kita hanya fikir kalau ada satu reactant. Okay. Then minus, there's a one bracket of which bracket tu dalam bracket yang kedua tu ada pengatas membawah. At the top is the concentration of your product power stoichiometric coefficient again. So contohnya dalam kes ni produk kita adalah B, right? So concentration of B power B tu adalah stoichiometric coefficient divided by Kc, equilibrium constant, tutup bracket. So the rate law is very specific. Kalau dia elementary rate law, ini adalah dia punya rate law yang very specific. Minus Ra equals to K in bracket, concentration of reactant, power stoichiometric, minus top concentration of product, power stoichiometric divided by Kc. Okay. If you notice, kenapa saya tak tulis CAE, CBE kalau kamu notice? Sebab dia bergantung rate law tu dikira pada masa bila tindak balas dia. If this rate law is measured at any time before equilibrium, sebab tu kita letak CACB, sebab kita tak boleh letak equilibrium, sebab kita kira rate law tu bila masa dia belum mencapai equilibrium. You can only write it as CAE, CBE apabila dia mencapai equilibrium. Okay, and then kamu kena ingat, pada equilibrium, CAE, CBE itu akan menjadi, minus Ra itu adalah kosong pada keadaan equilibrium. Okay, so that's why we don't write it as CAE, CBE, we write it as CA, CB. So kamu jangan confuse. Sebab rate law ni dikira pada keadaan sebelum dia mencapai keseimbangan. Just that yang tadi kita cerita pasal CAE, CBE, CCE, CDE itu adalah apabila kita nak kira Kc. Sebab Kc itu apa? Equilibrium constant. Sebab tu concentration dia mesti pada equilibrium. Okay. So next example adalah apabila, sekarang saya tukar rate law dia apabila ada two reactant, two product. Sebab tu bila saya ajar, I always have to consider, saya takut sudah confused. So saya bagi contoh yang pertama tadi, bila satu reactant, satu produk. This example, two reactant, two product. So apa berlaku pada rate law dia? So kalau this is elementary reversible rate law, is written as minus Ra equals to K in bracket, concentration of both of your reactant A and B, power stoichiometric A and B as according to your chemical equation, minus in bracket at the top concentration of your product C and D, power stoichiometric coefficient divided by Kc, your equilibrium constant. So then you get the rate law for reversible reaction. So now kamu dah cover part elementary reaction, reversible reaction, apa perbezaan dia? Perbezaan dia adalah pada rate law dia. So nanti kamu kena faham lah. Okay, apa beza dia? Kalau kita cakap pasal reversible ni, apa perubahan dia? Perubahan dia adalah pada rate law dia. So bila rate law dia berubah, kamu akan tengok desired equation pun akan berubah kan? Sebab kita ingat rate law berubah, desired equation pun akan berubah disebabkan rate law dia. Okay, so as a homework, okay, at the end of this chapter 4, I have one example. Alright, so this example, when you have extra time, I want you to go through by yourself this example sebab jawapan penuh semua saya dah beri. Yang penting is I want you to actually try to calculate it by yourself. Sebab tu saya beri jawapan sebab I would like you to actually really practice by yourself how to do the calculation sebab it's also a challenge, salah satu cabaran pemahaman. Cabaran kedua for student is sometimes student dia tak practice themselves. Tu bila kalau soalan sebenar dia dah tak sure cara pengiraan yang betul. Especially bila kalau kamu tengok complexity dia bila dia melibatkan pengiraan yang ada bracket and sub bracket. And this example actually has a quadratic equation yang kamu kena solve. So I want you to find, if you have time, definitely not today, if you have extra time, go through this question and try to calculate by yourself sebab soalan ni melibatkan quadratic. Okay. So if you don't understand, you can refer to me, but don't worry, dalam tutorial pun ada je soalan yang macam ni dalam tutorial. So we will do it again also in the tutorial. Okay, so that's all for chapter 4 and that's all for today lecture. For those tutorial LO1T2, kamu ada kelas petang ni 2.30, tapi don't worry, it's only about 1 hour class sebab ada hanya dalam 2 soalan, 3 soalan yang saya cover. So today evening class is not too heavy for you, about 1 hour, we will settle the question for chapter 4. But please make sure you attend the tutorial this evening. Okay, so that's all for today. I will see you next week for chapter 5. So thank you everyone and hope you have a good day today. Alright, bye-bye.